Hi there, I am Ember Quartz, digital persona at Kadel Labs. Welcome to our series on common production issues with microservices architecture. In this presentation, we'll explore the unique challenges organizations face with microservices and offer practical solutions to address them. In today's presentation, we will explore key challenges such as service discovery, API gateway performance, data consistency, inter-service communication, and monitoring and observability. Additionally, we'll discuss important aspects like security, scalability, deployment strategies, and dependency management. In total, we'll be covering over a dozen topics that address the most common issues and best practices for managing microservices in production environments. With that overview, let's dive into our first topic, service discovery issues. Service discovery helps services find each other, but the frequent changes in microservices make this difficult. Traditional IP-based methods can't keep up, leading to failures when services try to connect to outdated endpoints. To solve this, we use service discovery tools like Consul, Eureka, or Kubernetes DNS, which maintain a centralized registry of available service instances. There are two patterns: client-side discovery, where clients query the registry directly, and server-side discovery, where a load balancer directs requests. Best practices include self-registration and deregistration to keep the registry updated, and health checks to ensure only healthy instances are available. Additionally, using correlation IDs helps track requests across services, making it easier to debug discovery issues. By applying these tools and practices, we can manage service discovery effectively and ensure reliable communication between services. Next, we'll explore API gateway bottlenecks and latency. The API gateway is the entry point for all external requests to microservices, making it a potential bottleneck and single point of failure. High traffic and complex routing can cause latency and performance issues. This happens because the gateway handles tasks like authentication and load balancing, which, if overwhelmed, can slow down or crash, impacting all services. We can prevent issues by using rate limiting, caching, and distributing traffic across multiple gateways to avoid single points of failure. Load balancing and continuous monitoring of gateway performance help maintain system stability. Optimizing the gateway reduces latency and ensures efficient communication between clients and microservices. Next, we'll discuss data management and consistency. In microservices architecture, each service manages its own data, creating challenges in maintaining consistency across the system. This decentralized approach can lead to data discrepancies, especially during concurrent updates or transactions, as microservices don't share a single database. To tackle these challenges, we use distributed transaction patterns like the Saga pattern, which breaks transactions into smaller, manageable steps, or two-phase commit for coordination. Event sourcing, or CQRS, can also help maintain consistency by capturing changes as events and processing them in order. To ensure reliable services, design them to handle duplicate requests and regularly check data for inconsistencies. Use correlation IDs to track changes and help with debugging. By following these methods, we ensure data consistency and reliability in a microservices architecture. Next, we'll discuss inter-service communication failures. In microservices, services must communicate to fulfill requests, but this can lead to failures, especially in distributed systems. Network issues, timeouts, and dependencies can cause cascading failures where one failure affects others. These issues arise because microservices rely on unreliable networks. High latency, packet loss, or network partitions can cause requests to fail or time out, and excessive dependencies increase the impact of a single failure. To reduce these risks, we use retries with exponential backoff to handle transient failures and circuit breakers to prevent cascading failures by temporarily stopping requests to failing services. Setting appropriate timeout and retry policies and designing services to handle partial failures are also crucial. Asynchronous messaging can further decouple services, reducing failure impacts. By using these strategies, we improve the resilience of inter-service communications and prevent cascading failures. Next, we'll explore service versioning and compatibility. In microservices, services are independently developed and deployed, enabling rapid updates but posing challenges in managing multiple versions and ensuring compatibility. Versioning issues occur when different versions need to coexist, especially if services depend on specific versions. Without proper management, updates can break dependencies and cause system-wide compatibility problems. To manage versions effectively, we can use API versioning strategies, like embedding the version in URLs or HTTP headers, ensuring backward compatibility and smooth updates. Feature flags allow for gradual feature rollouts without impacting all users. Best practices include maintaining backward compatibility to avoid disruptions and using automated testing to detect compatibility issues early. Semantic versioning communicates whether changes are backward compatible, new features, or breaking changes. By adopting these strategies, we can effectively manage versions, maintain compatibility, and minimize disruptions. Next, we'll explore monitoring and observability challenges. In microservices, logs, metrics, and traces are spread across multiple services, making it hard to get a unified view of the system. Unlike monolithic applications with centralized data, microservices distribute logs and metrics across instances, complicating request flow analysis and problem diagnosis. To overcome these challenges, we use distributed tracing tools like Jaeger or Zipkin for end-to-end request visibility. Centralized logging solutions like the Elk Stack or Splunk help aggregate logs for easier search and analysis. Best practices include standardizing logging formats for better correlation and monitoring both technical and business metrics for a comprehensive view. Correlation IDs also enhance observability by tracing requests across services. By implementing these tools and practices, we improve visibility, detect issues faster, and maintain high availability. Next, we'll discuss security vulnerabilities. In a microservices architecture, the decentralized structure and many exposed endpoints increase the attack surface, making security a major concern. Each service has its own API and communicates over the network, creating potential security gaps. Vulnerabilities arise because network communication can be intercepted or tampered with, and diverse technologies across services increase the risk of unpatched vulnerabilities. To mitigate these risks, robust security measures are crucial. OAuth 2 and JWTs secure API communications, while mutual TLS, MTLS, ensures secure inter-service communication by authenticating both parties. Best practices include regularly updating dependencies, applying security patches, and using automated security scanning in the CI/CD pipeline to detect vulnerabilities early. Security audits and penetration testing also help identify weaknesses. By following these strategies, we can reduce security risks and protect our microservices architecture. Next, we'll cover resource management and scalability issues. Efficiently managing resources like CPU, memory, and storage is crucial for optimal performance and scalability. Issues arise when services compete for shared resources like databases, causing contention and reduced performance. Different services may also require unique scaling strategies. Some need horizontal scaling by adding instances, others vertical scaling by increasing instance power. Tools like Kubernetes help manage resources dynamically based on demand. Autoscaling policies based on real-time metrics like CPU usage ensure services get the resources they need without waste. Best practices include setting resource quotas to prevent overuse, regular performance testing, and monitoring to identify bottlenecks early. Allocating dedicated resources to critical services can further boost reliability and performance. By following these strategies, we can manage resources efficiently and scale services as needed. Next, we'll discuss deployment and CI/CD pipeline complexities. Deploying microservices is complex because each service has unique deployment needs, dependencies, and configurations. This can lead to challenges with dependency management, environment setup, and version compatibility. Without a strong CI or CD pipeline, manual deployments risk errors and downtime. To mitigate these issues, we use strategies like canary and blue-green deployments to safely roll out updates. CI or CD tools automate build, test, and deployment processes, ensuring reliability. Best practices include automated testing, using feature flags for controlled releases and versioning configurations to simplify rollbacks. These strategies help streamline deployments, reduce downtime, and ensure high service reliability. Next, we'll cover dependency management and version conflicts. Dependency management is a key challenge in microservices, as each service may use different versions of shared libraries, leading to version conflicts and compatibility issues. These problems occur because independent teams often select dependencies to suit their needs, resulting in multiple versions of the same library and potential runtime errors. To manage dependencies, using a centralized tool like Nexus or Artifactory is essential for consistent versions. Semantic versioning (SEMVer) helps clarify whether changes are backward compatible, new features, or breaking, aiding in better update decisions. Best practices include regularly auditing dependencies to remove outdated libraries, maintaining a compatibility matrix to track compatible versions, and automating checks in the CI/CD pipeline to prevent conflicts from reaching production. By following these strategies, we can minimize version conflicts and maintain a stable microservices environment. Next, we'll discuss handling stateful services in a stateless environment. In microservices, services are usually stateless, not retaining information about past requests. However, some scenarios like user sessions or transactions require managing state, which can be challenging in a stateless setup. This challenge arises because microservices are built for scalability and resilience, but retaining state increases memory usage and complicates request distribution, leading to potential bottlenecks. A common solution is to use external state stores like Redis, allowing services to remain stateless while managing state externally. For unavoidable stateful needs, sticky sessions can route requests from the same user to the same instance. Best practices include minimizing stateful operations to maintain scalability and designing stateful services with high availability to handle failures. Regular testing and monitoring are crucial to avoid state management bottlenecks. Performance optimization is crucial in microservices to ensure efficient use of resources. Shared resources like databases or caches can lead to contention where multiple services compete, causing performance issues. Contention happens when services simultaneously access shared resources. For example, several services writing to the same database table can cause lock contention, increasing latency. Poor configurations, like inadequate connection pooling, can also create bottlenecks. To optimize performance, we adjust service-specific settings like connection pools and use caching tools like Redis to reduce database load. Regular performance testing, setting resource limits, and continuous monitoring help maintain efficient operations and adjust to demand changes. These strategies help boost performance and reduce contention in microservices. Next, we'll discuss decentralized database reporting challenges. In a microservices architecture, each service manages its own database, enhancing scalability but complicating reporting that requires data from multiple sources. Unlike monolithic systems, microservices distribute data across various databases, making aggregation complex and prone to inconsistencies. To tackle this, we can use a data aggregation service to periodically sync data into a central repository or data lake for centralized reporting. An event-driven approach where services publish events on data changes also helps maintain an up-to-date copy of relevant data. Best practices include developing a tailored reporting strategy that combines real-time streaming with batch processing and ensuring data consistency across services. Using correlation IDs helps track data changes for accurate reporting. By following these strategies, we can effectively manage decentralized databases and generate comprehensive reports without compromising data integrity. To wrap up, microservices provide benefits like flexibility and scalability, but also introduce production challenges. We've covered issues like service discovery, API gateway bottlenecks, data consistency, communication failures, and service versioning. Careful planning and best practices are needed to maintain a reliable system. Thank you for your attention. I'm happy to answer any questions or discuss these topics further.